They forget to move. All right, make sure your name is please on the homework for today, the SHO kinematics handout. Just need your answers. Pass it to the right side. Make sure your name is on it. As always, please pass it to the right side. Put these guys away. All right, so with regards to the homework that you just passed in, and with regards to the problem that I did at the end of class last time, that's about as detailed as SHO kinematics gets. Yes, it's very tedious, but once you've seen the process once, and you've done a problem for yourself, number 2, for example, it's actually fairly straightforward. Before we move on, however, to SHO dynamics, that is exactly how F equals MA works. Just kind of hammering home here the idea to you that uniform circular motion and simple harmonic motion are very similar to each other. Let's take a look at the following elegant example. I'll also demonstrate it for you very easily. Go to your 6th period class. Return as soon as 6th period is over. All right. Do you have a 6th period class?
No.
All right, demonstrating the problem. Here's what is meant by oscillators being in phase and out of phase. Let's say that I have 2 identical oscillators. Now, if I set these oscillators into oscillation together, as we say, they are in phase. They basically oscillate together. If they're out of phase, as is described in this problem, it, for example, looks something like this. What we're given in the example is that the 2 objects, when they are at the exact same position, pass each other. They have a position plus or minus 1/2 the amplitude on either side of the equilibrium position. When they do so, they pass each other with the same speed. What we want to find is the phase difference, as it's called, between them. Now, initially, this looks like a very difficult problem, but as we'll see, it actually has a very elegant solution. But here's the basic description first. Okay, right here is our first oscillator. Our first oscillator here has a position x that's given to us as 1/2 the amplitude. And then it's moving, say, to the left-hand side here on my diagram with speed v. And then before I go any further, let's just give this guy a kinematics equation. So this guy here has a position with respect to time that's equal to the following. And then we have a second oscillator. It's completely identical to the first, it's just out of phase with respect to the first. So here's the second oscillator like so. Once again, the exact same position, x equals 1/2 a. but this guy's moving in the opposite direction, like so, with the same speed. So there is a phase angle here, there's a phase difference between them. So if this first one has a position equation that kind of looks like this, then the second one has a position equation that looks like this. That is where we have a phase angle. That's the unknown in the problem. That's what we're trying to find. Okay, now here's how to not approach the problem. I've seen this before. Students will say, okay, looking at these diagrams here, looking at these equations, let's note that the objects have the same position x. So what I should do perhaps is set the equations equal to each other, use some sort of trigonometric identity, for example, and try to figure out what the angle phi is. Then you'll run into a roadblock. Immediately in doing that, you run up against all sorts of complicated trigonometry. And then you would say, all right, well, let's see. These guys have velocities in the opposite directions. So this one here, his velocity equation looks like this. That's right. This one here, his velocity equation looks like this. So because they're passing each other in the opposite direction, what I can do is make one of them negative and set them equal to each other. Once again, do some sort of trigonometric identity to try to figure out what the angle phi is. You can ultimately do that to solve the problem, get the answer, but you're looking at a couple of pages of pretty complicated trig. You don't want to go anywhere near that. There's a very elegant solution that is literally just one step. If you remember that uniform circular motion and simple harmonic motion are very much the same thing. Here's a nice, elegant way of approaching the problem. So remember our comparison diagram, if you will, from last time in class. The oscillation occurs along the x-axis, and then right here is a circle to represent uniform circular motion. Okay, now the first oscillator, he's right here, we'll say. Remember the radius of this circle, by the way, is the amplitude A. So this right here is a position of 1/2 A. But now in terms of uniform circular motion, the guy up there on top moving to the left, let's kind of think of that as a first quadrant on this diagram. That is like so. We'll think of the object as here, moving counterclockwise in this direction. And then let me just form a right triangle here like I did last time in class. Like so, where the hypotenuse of this triangle is the radius A, the amplitude A. Notice that I can find this angle here very easily. Let's call this angle here theta, and I'll find it by just setting up a little bit of cosine. Notice that the cosine of that angle is equal to the adjacent side over the hypotenuse. The amplitude there, A, just cancels out, and you end up with the cosine of that angle is 1/2. Okay, now the cosine of what angle, by the way, is equal to 1/2? Yeah, 60 degrees. So this angle here is 60. All right, now that's the first oscillator, the one on the top board that's moving to the left-hand side. What about the other guy? Well, the other guy is also right here as well, but he's moving in the opposite direction. So think of that as the fourth quadrant on this diagram. Just think of it like this. So he's right here moving in that direction, like so. Or once again, I end up with the exact same right triangle now here in the fourth quadrant as I did a few minutes ago for the first quadrant. So because it's the exact same triangle, this angle right here in green is also obviously 60 degrees. This guy here is also theta. So then therefore, what's the answer? Right here is what we're looking for. This is the phase difference between them. This is the phi, the unknown that I wrote up on the top board. So what's it equal to? 120. Yeah, it's 120 degrees. It's literally a one-step problem once you make this comparison, once again, between simple harmonic motion and uniform circular motion. The 120-degree angle here is kind of hard to see when you compare two oscillators like so. It's kind of hard to discern from this, a 120-degree angle. The easiest way to think of it, though, is that the two objects are just in uniform circular motion, and as they circulate on the diagram like so, they're always 120 degrees apart. Nice little elegant way of picturing an example. Okay, by the way, I periodically give this to the AP kids on their oscillation exam every once in a while. maybe about 25% of them are able to get it right. A lot of them try something like this. All right, moving on from there. Nice way to warm up today. Now we get to SHO dynamics. Understanding how F equals ma when we apply it here gives us this motion and oscillation and how the kinematics equations come from it. So we're specifically going to apply F equals ma. Now, of course, we're going to do so for the simplest possible case. A simple harmonic oscillator, no heat loss, oscillating back and forth horizontally on a flat frictionless surface. So it's just our little basic picture as we've seen. Okay, now remember how the spring force works though. We have, first of all, the displacement x here, which we always think of as positive. Doesn't matter if we stretch or compress the spring. But then the spring force, or restoring force, always acts in the opposite direction, back towards the equilibrium position. Remember the magnitude of that force from Hooke's law is kx. However, it does point in the opposite direction of what we think of as positive. Therefore, we always give it a negative sign for that reason. Restoring forces like this, you'll see another one later on today, are always made negative for this reason. So then when I write down F equals ma here, this is the only force that matters. I don't have to worry about the normal force and gravity. They cancel each other out. There's no friction, etc., etc. So then therefore, when I write F equals ma, I just arrive at this expression here. Ah, very good. It does have a pass. Okay, see this? Came into class, the pass. It's not necessarily a problem in this class, but from now on, from here all the way until the end of the year, if you are tardy and you do not have a pass, you will be issued a detention. Make sure that you are present on time every single day. Okay, now getting back to F equals ma here, we have the spring force is equal to mass times acceleration. This is not an algebraic equation, however. The reason why it's not an algebraic equation is because as the position x is continuously changing, then the acceleration is continuously changing. It's a non-constant acceleration. So we can't solve the problem algebraically like we did throughout chapters 4 and 5, for example, to analyze the motion. This is not an algebraic equation, it's a differential equation. Instead, it's a differential equation. Now the word differential means derivatives. So where are the derivatives in this differential equation? Well, keep in mind that acceleration is the derivative of velocity with respect to time. Velocity is the derivative of position with respect to time. What that means is that acceleration is the second derivative of position with respect to time. The differential equation is written like this. Notice the notation here for the acceleration. It's the second derivative of position with respect to time. That's what this term here means. And now the question is, okay, well, how do we solve this differential equation? Well, the first thing to do is actually just algebraic. All I'm going to do is take the mass here initially first and just move it down to the left-hand side, such that I end up with the following expression. So now we kind of run up against the following question. How do we solve this differential equation? Well, solving a differential equation means the following. It means finding a function x, where if you plug it in here, and you take its second derivative, and plug it in here, the equation works. In other words, the equal sign applies. So we have to find a function. We have to find a function, x, as a function of time that fits into the equation. We actually already know what the solution is. We've last couple of class periods. Think of it this way. What function have we seen that has a form and its second derivative has the exact same form, but it's negative? In other words, starting with an x and then taking a second derivative, you end up with a negative x. What equation have we seen that behaves this way? Fourth period got it. Guys get
What
it?
did you say that again?
Okay, so what function have we seen for x that is some value where its second derivative is the negative of that value? Peggy? That's right, cosine. Because cosine, if you take its second derivative, is a negative cosine. Watch what happens if we write down the solution in the following way. The solution to this differential equation is just our position as a function of time kinematics expression. When I write this down, by the way, at this point a phase shift is kind of an unimportant mathematical detail. I'll just leave it like that. What I'm going to do now is take this equation, fit it into the left-hand side of the expression, and then I'm going to take its second derivative, just the acceleration, and plug it into the right-hand side of the equation. But first of all, just writing the derivatives. The first derivative with respect to time is just the velocity. So the second derivative with respect to time is just the acceleration. So let's fit this into the right-hand side of the expression, this into the left-hand side of the expression. And then here's what happens when you do this process. Okay, first of all, the left-hand side. So for the left-hand side, we have minus k over m, and then times x, which is this. And then on the right-hand side of the expression, we fit in the second derivative, just the acceleration equation, this guy here. So, and notice that a bunch of stuff here cancels out. Okay, first of all, the negative signs cancel. The amplitude A cancels. And the cosine cancels. So, and all that's left in the expression now is, first of all, here on the left-hand side, k over m, and here on the right-hand side, we'll make a square. Take the square of both sides to finish. So, we've solved the differential equation. Now, what the heck does that mean? You can follow my process here mathematically, but what does this say? What this is saying is that, yes, this equation here does describe the position as a function of time, the kinematics expression for simple harmonic motion. This is its velocity, this is its acceleration. This works, however, only if this is true. The angular frequency of the motion depends upon the spring constant K and the mass M. When you see this process done the first time, as I'm doing here, it almost kind of looks like that this just kind of falls out of the equation. So what is this guy here really saying? Where does this come from? Here's another alternative way of thinking of it. It first of all comes directly from solving the differential equation F equals ma. But another way of seeing why this expression has to work the way it does is to approach it from a slightly different angle. Approach it now from a conservation of energy standpoint. Think of it like this. Just erasing that. Now remember, for simple harmonic motion that the energy is conserved. It's a constant, it never changes, there's no heat loss. So now what I'm going to do is just pick an oscillator and look at two specific points in the oscillation. So first of all, let's look at what happens at the amplitude position. Right here is the amplitude position A, when the object has a speed equal to 0. Now let's describe the total energy, E, of the oscillator at this point. Now remember that in general, energy is kinetic plus potential. So if we jump back to chapter 8 for a moment, kinetic energy is 1/2 mv squared, and spring potential energy is 1/2 kx squared. So remember spring potential energy, for example, back from chapter 8. If, however, the object is at the equilibrium, or excuse me, at the amplitude position, the speed is 0, what is all of the energy here? Is it all kinetic or all potential?
Potential.
Yeah, it's all potential. So the total energy here is 0 for kinetic energy, plus then 1/2 kx squared, where the x is just the amplitude A. This expression that I'm writing down right here is the general expression that is always used to describe the total energy of an oscillator that consists of a mass attached to a spring. And now, secondly, let's just examine some arbitrary points in the oscillation. Negative sign squares out, a squared omega squared sine squared omega t. That's the first term. And then plus 1/2 kx squared. So plus 1/2 k multiplied by this guy squared. So when you square this, you just get a squared cosine squared omega t. So, give me a moment here to catch up. As you're doing so, looking at the expression, do you see a trig identity there? Yeah, sine squared plus cosine squared is equal to 1. However, are the coefficients here and here the same? No, so I can't use the trig identity yet, but right there, what we're going to substitute right there is this little expression that kind of seemingly popped out of F equals MA. Let's plug him, Jacob Quiet, onto here. So I've got the left-hand side of the expression, and now the right-hand side. First of all, this stuff, 1/2 MA squared. And then times omega squared. So that square root term over there, squared. Like so. And then just sine squared omega t, we can keep it as omega. And then the second term is untouched. First term here, the mass cancels. So now take a look. Do I now have the same coefficients in front of the sine squared and cosine squared? Yeah, so now, yes, I can factor it out. So then therefore, we just simply end up with this. Left-hand side, and now on the right-hand side, factor out the 1/2 ka squared from both terms. There's the trig identity, now in parentheses equal to 1. So yeah, the left-hand side of the expression is equal to the right-hand side of the expression. It has to be. It has to be because the energy is conserved. However, it will only work out if the angular frequency omega is equal to the square root of k over m. So what I'm doing here is I'm attempting to show you why this has to work the way it does in 2 different ways. Number one, it comes directly from solving F equals MA. It's almost as if it falls out of the equation. You end up with this expression. But this expression has to work. It has to work because the energy has to be conserved. That, after all, is what is being described here, a simple harmonic oscillator. So this is how I kind of show it algebraically by using conservation of energy. but directly by solving the differential equation, this guy here pops out of the solution. Once again, the first time you see this, it's a little bit confusing, but in general, that's how, or rather what we mean by solving a differential equation. Ariel, you had a hand up a moment ago.
Could we explain again how you want the blue line to the green line?
Okay, so by just plugging in my kinematics equations for x and v, I just get to this step right here. And then as I asked you, we can immediately begin to recognize here a trig identity. Sine squared plus cosine squared is equal to 1. But right here in the blue step, I can't do that directly because this coefficient here in front of the cosine squared is not quite the same thing as this coefficient here in front of the sine squared. But if I take what fell out of the differential equation earlier, omega as the square root of k over m, and specifically plug it into here and square it, like so, then it works out as it has to. This guy here has to be the same thing as this because the energy is conserved. The only way that that will work is that if this equation is true. We will, by the way, next week in class, verify this equation. Basically what this equation here says is the following. It determines why an oscillation happens the way it does. Here's the easiest way to think of it. I'll also demo it for you very nicely. So let's examine this angular frequency expression here a little bit more carefully. The easiest way for me to demonstrate it to you is not to think of it in terms of angular frequency, which is kind of hard to see, but instead think of it in terms of period, which you can see and measure with a stopwatch, for example. Now remember the period is 2 pi over omega. So if you plug this guy here into the denominator of the expression, you end up with this expression here for the period. As we'll see in a few minutes, this equation here, when it was first discovered, is not just important in the history of physics, it's important in the history of science and technology overall. I'll get to exactly why I said that, however, in a few minutes. But let me just explain what this expression says. It basically says that the period, and then therefore the angular frequency, depends upon two numbers. It depends upon how stiff the spring is, and it depends upon the mass of the object that's attached to the spring. So let me demonstrate this expression. I'm basically going to manipulate those two variables. I'm going to move these guys out of the way. Well, let me start by manipulating K, the spring constant. So I'm going to start here with a really loose spring. This guy has a really small K. If I've got a really small K, is the period a small number or a big number? So if this here in the denominator is small, what does it tell us about this here? It's big. In other words, the period is large. It takes a long time for the oscillation to occur. So think of it like this. So what I'll do is take this guy here and attach it to the spring like so. And now I'll set it into oscillation, like so. If we timed how long it takes for one oscillation, period, notice that it's a fairly large number. Now compare that period to, using the same mass, the period associated with this much stiffer spring. This guy here is much stiffer and has a much larger K. So if the spring constant is a large number, what does that tell us about the period? It's a small number. In other words, the oscillations happen quickly. This is a short period of time for an oscillation. So put this guy up like so, attach, and now set this into oscillation. Notice how short the period is. The frequency here is high. As we say, the period is short. So by manipulating the spring constant, we can begin to see easily how the expression works. We can also, however, manipulate the mass as well. What I'll do in this case is I'll go back to this really loose spring, like so. And now I'll start with a small mass, this little guy right here. So if the mass is small, what does that then tell us about the period? It's small as well. In other words, the oscillations happen fairly quickly. So with a small period, that just kind of looks something like this. And then compare this now to, once again, if we go back to this guy here. This is a large mass. So if we make the mass large, the period is large, it takes a long time for the oscillation to occur. So we attach, set this guy back into oscillation. Notice the period here is obviously longer than it was for the smaller mass. So basically, all of the dynamics of how an oscillation happens really depends upon two things: how stiff the spring is and the mass of the object itself. Notice what this equation, however, does not depend upon. It does not depend upon the amplitude. Notice that the period, and therefore omega, the angular frequency, does not depend upon the amplitude. This is extremely important. Before I describe that importance, however, let me just demo it. And what I'm going to do is just move back to this large spring, because it's easy to see, like so, with a large mass. And now what I'm going to do is set this guy here into a small amplitude oscillation, something that kind of looks like this. The total energy here is small, 1/2 Ka squared, but if I measured the period with a stopwatch here, like you'll do in a lab exercise, I would get some number. Let me now go ahead and set this into a larger amplitude oscillation, like so. In this case, there's more energy here. The 1/2 Ka squared here is a bigger number than it was earlier, but the time necessary for one oscillation here, if I measured it with a stopwatch, is exactly the same as the time necessary for one oscillation here. The period does not depend upon the amplitude. The reason why this equation is so important is because when it was discovered in the late 17th century, it led immediately to the construction of the first accurate clocks. All clocks, whether they be mechanical, electronic, or otherwise, have at their heart a timing element. That timing element is an oscillator. The reason why it acts as a perfect timing element is because the time for one oscillation has nothing to do with the amplitude of the motion at all. Now, there's no such thing as a simple harmonic oscillator. There is instead only what is called a damped harmonic oscillator. With a damped harmonic oscillator, energy is being continuously lost as heat. This means that the amplitude dies down. But as the amplitude dies down, the period doesn't change. The period of the oscillation here is exactly the same as the period of the oscillation here. Therefore, I can use an oscillator as a clock. The level of the precision of the clock is determined exactly by what the period is. So for example, if the period of this oscillator is 1 second, then I can use this as a clock to keep track of time to an accuracy of 1 second. The shorter the period, the higher the frequency, the more precise the clock. But all clocks have at their heart an oscillator. An oscillator can be used as a timing element. Now that's an example of a mechanical clock. Another simple example of a mechanical clock would be a pendulum clock. As we'll see later today, yes, a pendulum is a simple harmonic oscillator. Like with the mass attached to a spring, in the case of a pendulum, the period of the oscillation does not depend upon the amplitude. So then therefore we can use a pendulum as a clock. Now think of some of the electronic clocks that are around us, specifically our spark timers. We use spark timers in numerous lab exercises. What is the period on the spark timer? What's the period? You used it over and over. It's 1/60th of a second. Remember, the frequency is 60 hertz. Where does that time of 1/60th of a second come from? It comes from the alternating current. Because the alternating current is an oscillator. It has a frequency of 60 hertz. That is the standard that is used throughout the United States. Whenever you plug anything into a wall socket anywhere in the country, the frequency of the alternating current, the oscillator itself, is 60 hertz. Therefore, the period is 1/60th of a second. So our spark timers are precise to within 1/60th of a second for that reason. In other words, it's a pretty good clock. What are the most precise or accurate clocks of all? Does anybody know what they're called? Yeah, atomic clocks. Atomic clocks were invented back in the 1950s. Now, if all clocks have an oscillator, what is oscillating in an atomic clock? It's not the atoms. The electrons. How?
Between different orbitals.
That's right, between different energy levels. As those electrons oscillate between different energy levels, they oscillate with frequencies in the neighborhood of billions of hertz. This then means that the period of the motion is within billionths of a second. So then therefore the precision of an atomic clock is within billionths of a second for that reason. We actually no longer base time on the rotation of the Earth. Atomic clocks are actually more accurate as timekeeping devices than the rotation of the Earth. This was discovered when atomic clocks were first invented in the 1950s. The United States official clock is in a vault in Colorado Springs, Colorado, at a place called the National Bureau of Standards. This particular atomic clock uses an isotope of the element krypton. And the second is specifically defined in terms of the transition of electrons within that isotope of krypton from one specific energy level to the other. That's actually how we define the second today. Now, a couple of days ago, we had a leap year, right? What day is always associated with leap year? February 29th. How often does leap year occur? Once every 4 years. Okay, we've been using leap years in the calendar for more than 1,000 years. The reason why the leap year is there is because it doesn't quite take exactly 365 and 1/4 days to go around the sun. Excuse me, it doesn't take 365 days to go around the sun. It takes about 365 and 1/4. So that's why we had to add on an extra day at the end of February every 4 years for that reason, to account for that slight discrepancy. But how many of you periodically hear in the news where at the end of the year, usually at midnight on December 31st, we have to periodically add a leap second to the year? How many of you ever heard about this in news reports and so forth? The reason why is because we don't base time on the rotation of the Earth anymore. We instead base it on an atomic clock. So to correct for that discrepancy, periodically, once every couple of years, an extra second has to be tacked into the year to keep track of it. With the invention of atomic clocks, what we actually have discovered is that as the Earth rotates, it doesn't do so uniformly. It actually wobbles a little bit. The reason why it wobbles a little bit as it rotates is because the mass of the Earth is not uniformly distributed within the volume of the Earth itself. You know, there's the crust and the core and the mantle and blah, blah, blah. That non-uniformity actually causes the Earth to kind of wobble a little bit as it rotates. This is only noticeable, however, with the invention of atomic clocks. Now, how many of you use GPS technology? How many of you use a navigation program, for example, when you're driving? GPS technology is not possible without atomic clocks. Here's the basic idea as to how it works. In order for you to determine your geographic position, you basically need two numbers, your latitude and longitude. Finding latitude is the easy part. Latitude is basically found by looking at celestial objects in the sky at a specific time of day, like looking at the sun at noon, for example. The angle that it makes with respect to the horizon could be used to figure out what your latitude is. That's not that hard to do. The hard number to get is longitude. In order to find your longitude, you need to know two precise times. You need to know what time it is at your location, and you need to know what time it is at the prime meridian, 0 degrees longitude. Now, where is 0 degrees longitude? It's in Greenwich, England. It passes through Greenwich, England. It actually specifically passes through the mount of the telescope at the Royal Observatory in Greenwich, England. That's 0 degrees longitude. In order to tell what your longitude is, you need to know what time it is at your location, and at the exact same moment, know what time it is in Greenwich, England. If you know those two times, then it's actually a short amount of math to figure out what your longitude is. So how does the GPS system work? The GPS system is actually a series of satellites, about 24 or so, that are orbiting the Earth at different altitudes and at different orbital inclinations. Aboard each one of those satellites is an atomic clock. All those atomic clocks are synchronized with each other. They're passing radio signals back and forth between each other, and they're passing those signals then down to your phone. Only by keeping track of time very precisely can you then determine your geographic position very precisely, to within, for example, a couple of centimeters, latitude and longitude on the surface of the Earth. That's how GPS technology works. And then when you use an app, like Waze or something like that, then the app just updates in real time continuously by getting that signal from the atomic clocks in orbit. That's how the GPS technology works. It's not possible without keeping track of time very precisely. Let's take a short break here.
Short yield up 2 points today. Short 430 now.
Something similar to your first match. Yeah. And then multiply that with 0.25 cube. You have to make it into
It's like a massive here.
Okay, now you're not fading back here, right? You're not falling asleep on me, right? Claire?
You want to bring rice?
Done the polar seals.
Bring rice. Like plain white rice.
How?
You can't sell it.
Oh, no.
We only have one problem.
You have the homework book for that, the first part, and then the back part, there's like 12 different equations. Plus you have like a bookwork or something like that. I have like 5 extra problems.
Yeah, it's like these black so we're gonna bring all the shit next time. Should we go first?
Nah.
Let's play the rice game. We get rice. We actually practice. And then like we'll do all this stuff, and then we'll get a good grade, or else we'll like extra. But I feel like the first time we're
Yeah, I don't like saying all the time.
today.
I'm being dead
The last 20 minutes we watched it.
Katie was so bitter when she got 100% of it. So it's like,
And he pushed back the test. We just
oh, I didn't
it's supposed to be tomorrow. What else? You guys do play? We should do next week.
I remember it was like it's like
What do we do?
It's
say 1
All right, please take a seat. Please have a seat, Howard. Okay, before we move on to what is called a simple pendulum, just because of tomorrow's web assignment I want to briefly here tackle 3 pretty easy problems that are all quite short, but you basically have to see these problems done in order to understand some of the web assignments that are due tomorrow, for example. Usually with these last 3 examples here, what you do is take what is given there in words and write it out as a simple mathematical expression. All 3 of these problems, as we'll see, are all pretty short and simple. Yeah, definitely. All these problems, these 3 here, they all kind of work the same way. That is, given what is there in words, and write it out as some sort of mathematical expression. In this first of the 3 examples, we're comparing 2 oscillators. As you'll see, we're basically given 2 ratios and find the third. All right, so first of all, I've got these 2 oscillators. Let me just describe one of them first. Okay, so right here is the first one. It has an amplitude, we'll call it A1 associated with its motion. There's a spring constant, we'll call it K1, and it has a total energy, E1. Now, from a little while ago, remember that the total energy of an oscillator is 1/2 Ka squared. So the energy of oscillator number 1 is 1/2 K1, A1 squared. And then we've got our second oscillator. Let's just describe that guy as well. So our second oscillator has a different amplitude, A2. It's got a different spring constant, K2, and it has a different amount of total energy, E2. So before we get to the comparison now, let's just write down his energy equation, 1/2 K2, A2 squared. So I'm just describing these 2 guys here first. And now I just take what is given there in words and write it out as a mathematical expression. So it says, first of all, that the first oscillator has 10 times the energy of the second. So the energy of the first is 10 times the energy of the second. So it's a 10-to-1 ratio. We're also given another ratio. The spring constant of the first is 2 times that of the second. K1 is 2K2. So we're given these 2 ratios here, and we basically just have to find a third. Third has to do with the ratio of the amplitudes. To do that, we just write down these total energy expressions into here, what is given. So we first of all have E1. So that's 1/2 K1 A1 squared. That then equals, on the right-hand side of the expression here, 10 times the energy of the second. 10 times 1/2 K2 A2 squared. Like so. And now before I start canceling some stuff out, we have one more ratio that's given, the ratio of the spring constants. So therefore, let's replace right here this K1 with a 2K2. And at this point, we're just about done. Because now at this point, a bunch of stuff starts to cancel out. So when I start some canceling here, first of all, the 1/2s on both sides of the expression cancel, like so. Okay, a 2 cancels here and here, thereby making this a 5. And lastly, the K2s cancel here, here. And now, if I just kind of clean up what's left over, I have this, like so. And then just take the square root of both sides to finish. So the ratio of the amplitudes then depends upon a there's a WebAssign problem that is very similar to this. That's basically how you approach it. We're given two ratios, you find the relationship between them as I've done, and then you find the third ratio. And the last two are very similar to each other. I kind of put them both here on the same page because they are similar. They're similar in the sense that what we do is take, once again, what is given there in words, and then just write it out as a basic mathematical expression. So I'm going to call these problems here 1 and 2. Go ahead and write them both down. Once again, I put them on the same page because they're pretty similar to each other. And then for the spring potential energy. So here on the left, 1/2 of 1/2 Ka squared. And then on the right, just 1/2 Kx squared. And now you solve for x. So let's see if you're correct. All right, well, first of all, I can cancel a 1/2 from each side. I can cancel a K from each side. So, and now if I just kind of clean up here what's left before I do the last step. Here's what I have left after canceling. So are you correct? Is the answer 1/2 A? No, not quite, because now we have to take square root of both sides. Yeah, it's actually 1/√2 times A, like so. So it's intuitive to guess that it would just be 1/2 the amplitude. Not quite, however, because of the square relationship. Once again, an easy problem. Once you realize what's being asked, you just have to write out the words in math. Same thing with the last one. With respect to the last problem here, it's almost literal. Think of it like this. What fraction of the total energy is the spring potential energy if the position is 1/2 the amplitude? So notice how I took what is there in words and just wrote it out mathematically. So I have to figure out what this fraction is, what this number is. It's a percentage. I have to figure out what that is when that happens. So now here in the numerator of my fraction, just write spring potential energy. In the denominator of the expression, write total energy. So, and the 1/2 K's just cancel out. This. And then lastly here, just plug in the x as 1/2 1/4, it's 25%. So then at this particular position, 1/2 the amplitude, then 1/4 of the energy is potential energy. What would be then the fraction of kinetic energy? 3/4, okay? So that's how you approach those problems. You'll see stuff similar to this in WebAssign. Usually they're all pretty easy, you just have to realize exactly what it is that's being asked for. Okay? All right, so I wanted to tackle those here briefly before we move on to today's last topic. First. Okay, let me set it up immediately as a demo. Get rid of this guy. And instead, what we replace with a mass attached to a string. And I'll arrange it now as a pendulum. Like so. We talked about pendulums back in chapters 7 and specifically chapter 8, which I used to illustrate gravitational potential energy, if you remember, and conservation of energy. We did a couple of pendulum problems where we had the energy transfer back and forth. We never went through, however, how F equals ma gives us this motion, and then the kinematics of this motion. Obviously, this is an oscillator. It's referred to as the simple pendulum. What I need here to do first is to show that the simple pendulum is a simple harmonic oscillator. So I first want to prove that the simple pendulum is a SHO. Okay, that means that I'm going to apply F equals ma here to this situation in just a moment. But here's kind of the direction that we want to go. Let's just jump back to earlier today. For a mass attached to a spring, this was our differential equation for simple harmonic motion. The angular frequency of the motion was the square root of the constants there, the square root of the k over m that appears here in front of the position. Anytime you set up F equals ma and get an equation that looks like this, stuff times position equals the second derivative of position, it means it's a simple harmonic oscillator. The angular frequency of the oscillation is always the square root of the constants here that appears in front of the position x. So my approach here for the simple pendulum is to set up F equals ma and see if I get an equation that looks like this. In other words, stuff times position equals second derivative. If I do, then it is a simple harmonic oscillator. That's what I'm trying to prove here. Okay, now with respect to the simple pendulum, immediately we start to use terms here like we do for an oscillation. So let's just think of, for example, the vertical position here as the equilibrium position. And then we'll draw it back like so, forming an angle with respect to the vertical direction. And then release it so it begins to move along a circular arc. That will give us something then that kind of looks like this. So here's our mass M. Here's the length of string L. Okay, here vertically downwards like so. This right here is the equilibrium position. And then as the object is oscillating back and forth, it is doing so along a circular arc. Let's think of that circular arc like so. Position x, which we'll think of as positive away from the equilibrium position, just like we do with a mass attached to a spring. Right here is an angle that is made by the string with respect to the vertical direction. Let's call this guy theta. Now, there are only two forces acting on the pendulum. It's just tension and gravity. So our force diagram is very simple. It just looks like this. Here's the tension T. Here's mg. But unlike the conical pendulum back in chapter 5, what I'm going to do here is not take the tension and break it into components, but instead I'm going to take the force of gravity and break it into components. I'm going to break it into components like so, and like so. Where right here is the angle theta. Now as the object oscillates back and forth, yes, it is oscillating along a circular arc. So technically speaking, there is a centripetal acceleration inwards towards the center of this imaginary circle. In other words, on my force diagram, it's in this direction like so. Frankly, we don't care. The reason why we don't care is because what we're trying to describe here is what's going on along the circular arc. In other words, due to this mg sine theta right here, that causes an acceleration along that circular arc. That acceleration is referred to, by the way, as a tangential acceleration. So we're not going to worry about adding up the forces this way. We're only going to worry about adding up the forces this way, because in this direction, that's then what causes this acceleration that we're worried about. So I now write F equals ma then in the following way. It's just mg sine theta equals mass times acceleration. So, once again, we use the same terminology here for the simple pendulum, though, as we do for a mass attached to a spring. We still think of the displacement as a positive number. Notice, however, that the force vector here, mg sine theta, is back towards the equilibrium position. It's a restoring force, just like the spring force is. So we give it a negative sign for that reason again. So the negative sign is here because mg sine theta is a restoring force, just like the spring force is. You know, let me just cancel out the mass. Mass always cancels when talking about gravity. And we end up with this. Is this an algebraic equation? No, it's not. Because on the left-hand side, what is continuously changing? Yeah, the theta is continuously changing. So as the angle changes, the A changes. So it's not an algebraic equation, it's a differential equation. The acceleration here is, once again, the second derivative of position with respect to time. Looks like this. Now pause here for a moment. Just look at this expression and look at this one here. Do the equations have the same form? Not quite. We do have a second derivative here on the right-hand side, but we need stuff times position equals second derivative. We don't quite have that here on the left-hand side of this expression. So I have to make some adjustments to the left-hand side. It's just two small steps. The first adjustment that we make is just like for the conical pendulum, here we make a small angle approximation. Now I know it's been a while since we've seen the small angle approximation, but with the small angle approximation, remember that three numbers are basically the same thing. The angle, the sine of the angle, and the tangent of the angle. If you guys remember, I actually had everybody take out their calculators. I think we used 15 degrees as the angle. We converted it into radians, and then we took the sine of it and we took the tangent of it. And we found that all three of those ratios were exactly the same thing. We do the same thing here. So I replace the sine of theta with just the angle theta. So. Well, this is a little closer to what I'm looking for, but it's not quite exact. Once again, I'm looking for stuff times position equals second derivative. So I have to make one more adjustment, and that's the angle. The angle itself, right here in my diagram, is equal to arc length divided by radius. Go all the way back to virtually the very first day of class. I'm talking about Eratosthenes' calculation, radian measure, arc length divided by radius is equal to angle. Place that here, like so. Arc length over radius. So now take a look at it. Does this equation here have the same form as that equation over there? Yeah, so it's a simple harmonic oscillator. However, the angular frequency is not the square root of k over m. Instead, the angular frequency is the square root of g over l. This guy right here. This shouldn't be all that surprising. Yes, obviously a simple pendulum is a simple harmonic oscillator. Let's get a handle on what this little guy here is saying. We demonstrated it. Like I did earlier for the mass attached to the spring, however, let's not think of it in terms of the frequency omega. Let's think of it in terms of period. The period is 2 pi over omega. So if you take this guy here and stick it into here, you end up with this expression. Notice that the period of the motion just depends upon the length of the string. So watch me manipulate the length of the string here. For example, let's say that the length of the string is small. So here's a small L. If the L is small, what could you say about the period, capital T? It's small as well. So it takes a short amount of time, in other words, for one oscillation to happen. But now let's make the L big, the whole thing, like so. So if I make the L big, what can I then say about the period, capital T? Now it's big, so it takes a long time for an oscillation to occur. So small L, short time. Big L, big time. Easy enough. Notice that like a mass attached to a spring, this does not depend upon the amplitude. So the amplitude being small, for example, like so, or the amplitude being a little bit larger, like so, has no effect on the period. You'll verify this in our lab exercise next week. So what we'll do is measure the time with a stopwatch, for example. We'll then verify that equation directly. Now, with a really small amplitude, yeah, the energy here is small compared to the energy here, but the time necessary for one oscillation in both cases was exactly the same. So can we use a pendulum as a clock? Absolutely. The very first mechanical clocks that were made were basically pendulum clocks. Obviously, a grandfather clock is a pendulum clock. It's using this equation directly. By the way, you've seen this equation before. You actually did a lab exercise back in the first semester that verified this equation where you measured small g. What lab exercise was that? Does anybody remember? It was the conical pendulum. The conical pendulum has the exact same period. Before I show that, it's actually obvious why this is. Compare pendulum like so and a conical pendulum like so. In both cases, it's the same two forces, tension and gravity. So because it's the same two forces here as it is here, it should give us the exact same kinematics. And as we've seen over and over and over throughout this unit on oscillations, what do we know mathematically about uniform circular motion and simple harmonic motion? It's basically the same thing. So then therefore the periods should be the same. Let's see if they are. Nice little bit of review. Back to the good old days of chapter 5, right? So recall the conical. So remember the conical pendulum, by the way, just to demo it once again here quickly, is when the object is traveling in uniform circular motion, the circle is parallel to the ground, and we have a centripetal acceleration that's inwards towards the center of that circle. Remember how it's kind of drawn out, it kind of looks like this. So here's our pendulum of length L, mass M, here's the vertical direction, here's the right triangle, here's the angle theta, right here is the radius, and then the circle, remember, is perpendicular to the board. Remember how we draw this, kind of comes out of the board, goes into the board like so, and then right here is the centripetal acceleration vector when the object is here on the left. And then the centripetal acceleration vector points towards the center of the circle. Okay, same two forces though as it was with the simple pendulum from a few minutes ago. Tension and gravity. Tension and gravity. But in this case, the acceleration vector is horizontal towards the center of the circle, which was over here. So then, like we did back in chapter 5, we take the tension here and break that into components, like so. Right here is the angle theta. And then we started to add up everything using F equals MA. When we did the conical pendulum, by the way, the reason why you're taught the conical pendulum first before the simple pendulum here today is because F equals MA for the conical pendulum is not a differential equation, it's an algebraic equation. It looks like this. T cosine theta cancels out with mg. And then T sine theta equals MA. The acceleration, keep in mind, however, is the centripetal acceleration, the speed squared divided by the radius, inwards toward the center of the circle. And then we combine the equations together algebraically. I solved for t in the top expression, so divide the cosine to the other side. So take that expression for the tension and plug it into here. And this is all just algebra, that's why you see this in chapter 5. So, mass cancels out, no surprise. Left-hand side of the expression, sine over cosine, tangent. Like so. And then we got to this step here, and like a few minutes ago that I did with the simple pendulum, we made a small angle approximation. In this case, we wrote the tangent of the angle as not r over the adjacent side. Instead, we wrote it as the sine, r over the hypotenuse, like so, r over L. Now, here on the left. And then on the right-hand side, we replace the speed v with the circumference of the circle divided by the period. Just keep in mind it's the period now, not the tension. We plugged this guy into here and squared it, and canceled out an r, and we did. We got this. And then the radius here cancels from either side of the expression. And then we cross multiply to solve for t squared. And we did, we got this. And then we did our lab exercise. Now what we did in that lab, for conical pendulums of length L, we measured the period with your stopwatches. We then plotted t squared versus L. We got a line. The slope of the line was 4 pi squared over g. We then measured g. You'll do the exact same thing next week, but in this case for the simple pendulum. Because if I now just take the square root here of both sides, there's the equation once again for the period of the conical pendulum and the simple pendulum being the same thing. So next week in class, in the lab, you'll measure g in this class for the last time. You'll measure g by just setting up a simple pendulum situation. Basically, for pendulums of length L, we'll measure the period, we'll plot t squared versus L, get the slope of the line, use the slope of the line to figure out the g. It's basically the same lab exercise. It's a lot easier to do, however, even than the conical pendulum with the simple pendulum. So no surprise, the periods are the same. They should be. It's the same two forces, gravity and tension, oscillation, uniform circular motion, being the same periods. There's just one last little minor detail about the simple pendulum before we finish today with just one kinematics example of it. So just one little minor detail here about the simple pendulum. Okay, so just getting back to that little diagram, that basic description of it. Equilibrium position vertically downwards like so. And then here's our position x like so. Here's our angle theta, like so. So our value of the differential equation was this, F equals ma. And then remember that the angular frequency omega is the square root of g over L. But once again, because this here has the same form as the differential equation for a mass attached to a spring, stuff times position equals second derivative, yes, it's a simple harmonic oscillator. So that then means that if we really wanted to, we could describe the position here, x, of the oscillator as a function of time. It's the exact same kinematics equation as it was for the mass attached to the spring. Like so, once again, without a phase shift at this point, that's just an unimportant minor mathematical detail. But of course, it has the same position. However, there is one slight difference when describing the position of a simple pendulum as opposed to the position of the mass attached to a spring. We typically don't describe the position of the pendulum in terms of x as a function of time. Instead, we typically describe it in terms of the angle made by the string with respect to time. So we adjust the equation slightly to reflect that. We basically write it in the following way. Remember that angle is arc length over radius. The angle is arc length over radius. So the arc length here on the left-hand side of the expression is the radius multiplied by the angle. And then on the right-hand side of the expression, we have, first of all, the amplitude A. That's just the largest value of x from the equilibrium position. The largest value of x, however, corresponds to the largest value that the angle is made by the string with respect to the vertical direction. It's sometimes called the amplitude angle. It's referred to sometimes as theta max or theta naught, etc., depending upon which textbook you look at. But we can think of that then in the following way. Once again, angle is arc length over radius. So then therefore the arc length is equal to the angle times the radius. So the radius times the angle, like so. And notice that the length of the string cancels out. So typically the position equation that describes the position of a simple pendulum as a function of time is this expression here. So we typically describe the kinematics of a pendulum a little bit differently as opposed to the mass attached to the spring. This is an easy equation to use, particularly without a phase shift. But the first time that you see it in an example, it's a little easy to get confused about what's what, because there's actually two angles. There's, first of all, the physical angle that you can see, the angle that is made by the string with respect to the vertical direction. That's typically thought of being in terms of degrees. But then we've got another angle here. This right here is in radians. This is describing the cosine curve of the oscillation. You don't see that angle. This is the angle that you see that the string makes with respect to the vertical direction. This angle here, however, is describing the oscillation. That initially sounds a little bit confusing, but when you see it in a basic example, it's straightforward. So let's finish today with this. Okay, without a phase shift, a problem such as this is really simple and straightforward, but we just got to be careful about what's what. Okay, so the two numbers that were given there is, first of all, L, the length of string, 2 meters. And then the amplitude angle, as it's sometimes called, the initial angle theta naught, and naught, of 15 degrees. Okay, but first of all, part A. In part A, all that we're working with is the angular frequency expression for a simple pendulum, the square root of G over L. When we plug everything in, the units work out to be radians per second, as they always do. So just plug in. So we then have the following. Square root of 9.8 divided by 2 meters. This works out to be about, and I'll write it out as a decimal, that's fine, 2.21 radians per second. Once again, even though we're talking about the angle made by the string in terms of degrees, in terms of the oscillation, the angle is still in terms of radians, hence radians per second. Okay, then calculate the period, just 2 pi over omega, easy enough. In this particular example, however, we end up with kind of a similar number, so just be a little bit careful about what's what. This is about 2.84 seconds. So this is a time, this guy right here is the angular frequency omega. Okay, part B now is just writing down the kinematics equation, nothing more than that. So the kinematics equation, that the angle that is made by the string with respect to the vertical direction is the following expression, nothing more than that. And therefore, we have here 15 degrees times the cosine of 2.21 times t. But there are two angles here in this expression. You just got to be careful about what's what. This angle here is the angle made by the string at its biggest value. And this is then therefore the angle that is made by that string as time goes on. This angle here is describing the oscillation. It's in terms of radians, as it always is. But that's how the expression works. And then lastly, take a look at C. Depending upon how it's phrased, this can actually be a little bit tricky. So think of it this way. Let's say that I draw the string back like so, so it forms a 15-degree angle. And then I let go. Now, how many times per oscillation is the angle made by the string here with respect to the vertical direction? 10 degrees. How many times per oscillation? 4 times. It makes an angle of 10 degrees 4 times, twice on either side of equilibrium. So it kind of looks something like this. Draw back to 15, and 10, 10, 10, 10, and then back to 15. It actually does it 4 times. So you have to be a little bit careful about how a problem is phrased when describing the kinematic pendulum. So I'm just going to keep it easy. I'm just going to calculate 2 times. We'll say here on the left, like so, my left is positive. Let's say here on my right is negative. So just think of it that way. But if it's phrased, depending on how it is, they may be asking for 4 times as opposed to 2. I will always be very explicit about it, don't worry. But there is initially a little bit of confusion associated with this. Now I can begin to picture that by just graphing out here quickly, or sketching the angular position theta here as a function of time. And it's just our cosine curve, like so. Where here is the amplitude angle, positive in one direction, and negative in another. And then right here I've graphed out a full period, as we always do, 2.84 seconds. Like so. So if I just think of it as positive 10 degrees, that's why I stuck the plus sign there. If I think of it as positive 10 degrees, then we're just looking at this right here. So I'm just going to find these 2 points, here and here, and without a phase shift, this is really easy to do. So to finish the example, we just jump over to here and plug into the left-hand side, just 10 degrees. Like so. And then just to finish here in a moment, I'll go ahead and solve for t. Do I, by the way, have to take this 10 degrees here and the 15 degrees here and convert them into radians? Do I have to worry about that? No. This could be anything. It could be degrees, meters, light years, whatever. It could be anything. However, this here is in terms of radians, because that's describing the oscillation. So I'm still in radian mode in my calculator to solve for this time, because I'm dealing with this angle in radians. This stuff here doesn't matter what it's described as. So I'm just going to divide the 15 to the other side. It's actually 2/3 when you do it. Inverse cosine of 2/3 equals then just 2.21 times t. Like so. So it's an easy problem. Once again, you just have to realize what's what. So finishing it off, let's see, divide by 2.21. And I get here this first time, 0.38 seconds. So you guys tell me, is that left or right for 0.38 seconds based on this number here? Yeah, left, obviously. Could I just use symmetry here to find the second time? Yeah. No phase shift, so I don't have to worry about that. So the T2 is 2.84, full period, minus what was that, 0.38? So, and then gives us 2.4 minus 0.38. That's about 2.46. Easy enough. Really simple pendulum, it's very straightforward. Excuse me. All right, so let's see, taking a look here at the agenda board, nothing specific will be collected next time on Monday of next week. There is a WebAssign, however, due tomorrow. The examples that I did today are very similar to a bunch of those WebAssign problems. It's a very easy assignment. Okay? Then when we do return next week, we've got our major laboratory exercise, chapter 14, our lab on good? Yeah.